Alright guys, so in this video we are going to be looking at our next type of naming, which is called covalent naming. This is the last type of naming that we're going to be doing before our naming and bonding test right before winter break. So in this type of naming, here are just a couple of characteristics of it. First and foremost, in covalent naming, we are looking at just covalent bonds, and because we're looking at covalent bonds only, these molecules molecules are only going to have nonmetals in them and metalloids in them. We're not going to see any metals or polyatomic ions. And because we're not seeing any metals or polyatomic ions, there's going to be no need for us to deal with the charges. So in all of the other types of naming we've done so far, remember you found the charge and you've crisscrossed the charges and rewritten them as the subscripts. This is going to be a complete 360 from that. We're not dealing with charges at all, but instead when you look at the molecule itself, however many atoms there are, you are going to use a prefix, which we'll go through in this video, to denote how many atoms of that element there are in the molecule, or vice versa. If you're looking at the name, the prefixes will be there to tell you how many you have when you're writing your formula. Before we get too far into our big covalent molecules that we're going to be looking at, there are a couple of elements that we need to talk about. So generally, when we're thinking about an element, most elements by themselves are going to occur as just a single atom. So when you see sodium and we talk about sodium, we're talking about a single atom of sodium. When we see aluminum, we're talking about a single atom of aluminum. When we see carbon, we're talking about a single atom of carbon. There are, however, some exceptions to this because there are always exceptions in science classes. So the first thing we're going to learn about are what we call the diatomic elements. And what this means is that when these elements are by themselves, they come in pairs. So they pair up with another atom of the same element. And we have a saying that will help us remember these diatomic elements. There are 7, and the saying is Brinkelhoff. And so what that means is bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, and fluorine. When these 7 elements are by themselves, they naturally pair up with another atom of the same element. So if we were talking about bromine, we're really talking about Br2. If we're talking about iodine, we're talking about I2, and so on with the rest of these diatomic elements. There are also 2 elements that we call polyatomic elements. Remember, these are different than polyatomic ions. So again, these are when elements are by themselves. They too pair up with other atoms of the same element. And there's only 2 of these. The first one is sulfur, and the second one is phosphorus. When sulfur is by itself, it comes in 8s, and the way I remember that is if you were to finish the S from sulfur, I'm going to do it in a different color. If you were to just close that up, we would have an 8. And then phosphorus, when it's by itself, comes in 4s, and I remember that because to me it looks like a 4 is just a backwards P. So these are some exceptions to the idea that most elements come naturally by themselves, and these are exceptions that we need to know. So now let's take a look at a whole covalent molecule that's made up of atoms of different elements. And so the first thing we need to know before we start naming these covalent molecules is these prefixes, because remember, these prefixes are going to be the things that we use to denote how many atoms of each element are actually within that compound. So most of these should be pretty familiar to you, but we're just going to run through them real quick. So the prefix mono means 1, di means 2, tri 3. This is one that a lot of students mess up. So tetra means 4. A lot of people try writing quad instead of tetra, but tetra is 4 in chemistry. Penta is 5. Think about it like a pentagon. Hexa is 6. This is another one. I'm going to put a star next to it that a lot of students want to write something different. So hepta is 7, not septa. It is hepta. Octa is 8. Nona 9, and deca 10. So we should be familiar with these prefixes already, but if not, you want to make sure that you write them down and that you become very familiar with them throughout the course of this video. So here are the general rules for naming covalent molecules. So the first thing we're going to be looking at is the electronegativity of the atoms. And remember, when we talked about periodic trends, we know that electronegativity increases as you go up a group and increases as we go across the periodic table. So we end up having an overall trend that looks like this. And so when we're writing our covalent molecules, you usually start with the least electronegative atom. And on your periodic tables that you'll be receiving with the rest of the year, those electronegativities should be on them. The next thing you're going to do is you're going to add the prefixes that we talked about on the previous slide to indicate the number of atoms of each element that are present in the compound. And there is an exception. So if there's only one atom of the first element in the molecule, we don't use the prefix mono. So if there's only one of the first atom in the molecule, you just omit it. You don't use it at all. And then lastly, similar to our binary naming, we're going to change the end of the second element in the molecule to ide, I-D-E. So let's walk through these practice problems together, and then you'll be asked to do a couple on your own. So starting us off, looking at the first molecule here, we have CCl4. So we have 1 carbon, and we have 4 chlorines. And remember here, all we're doing is looking at the number of carbons. So when we're looking at carbon, since we have 1, we would typically use the prefix mono, but since the carbon that is a single carbon is the first element in the compound or in the molecule, we omit that mono prefix, so we just have carbon, and then the prefix for 4 is tetra, so we have carbon tetrachloride. Looking at the next one, we have 2 nitrogens followed by a single oxygen. And so since we have 2 here, now we do use the prefix because our first one is no longer just 1. So our prefix now is going to be dinitrogen. And notice how the name of the first element stays just the same, so dinitrogen. And now since we have a single oxygen, and that single oxygen is not the first element in the molecule, we do use the prefix mono. So we have dinitrogen monoxide. And generally, if the root of the element name that you're looking at starts with a vowel, like oxygens or iodines, then you usually omit the second O. You don't double it. So it would not be monooxide or monoiodide. It would just be monoiodide or monoxide. But that's really just takes practice. So don't worry if you're not getting those right away. Looking at number 3, we have 3 sulfurs followed by 6 fluorines. So our prefix for 3 was tri. So we have trisulfur followed by hexafluoride. Trisulfur, spelled that wrong. Trisulfur hexafluoride. All right, so now we've gone from formula to name. Let's look at going the other way. So arsenic trichloride, because there's no prefix here, this tells us that we're looking at just 1 arsenic. So we have AS. And then trichloride tells us we're looking at 3 chlorines. So again, we're not dealing with charges, we're not dealing with crisscrossing. Whatever the prefix is telling us that's how many atoms of that element are in the molecule. So let's look at the next one. Dinitrogen pentoxide tells us we have 2 nitrogens and 5 oxygens. And then lastly, tetraphosphorus decoxide tells us we have 4 phosphoruses followed by 10 oxygens. So something that's different in covalent molecules than what we saw in ionic molecules, such as binary and ternary naming, is that we can never reduce the subscripts in covalent naming. Because we're no longer looking at a ratio of the atoms, a ratio of how many we need to cancel out charges. These prefixes are telling us exactly how many of each atom we have. And if we started to reduce the ratio, or if we started to reduce the subscripts, we would no longer have that same element. All right, so now that we know how to name covalent molecules, let's look at another property that we see in covalent molecules, and that property is called polarity. So there are two different types of covalent bonds that exist. We've got nonpolar covalent bonds and polar covalent bonds. In nonpolar covalent bonds, the electrons in the bond are shared equally between the two atoms. That make up that bond. Whereas in polar covalent bonds, it's the exact opposite. Here, the electrons in the bond are unequally shared. Between the two atoms. And what that means is that in polar covalent bonds, one of the atoms is more electronegative than the other atom. It wants that the electrons a little bit more badly than the other atom, and so it'll have a stronger pull on the electrons, which creates a partial charge in the bond, which is what we see here. So this little lowercase delta in Greek is what we use for a partial charge. So we have a partial negative charge and a partial positive charge that results from polar covalent bonds. One way I think about this is thinking back to our homecoming pep rally. So in the homecoming pep rally, we did a series of tug-of-wars between the different classes. So in the nonpolar covalent bond, those electrons are going to be pulling with pretty equal strength. And so this would kind of remind me of a tug-of-war game between the seniors and the juniors in terms of strength and size and being able to pull on the rope. Both classes are going to be pulling on the rope pretty equally. Whereas when we're thinking about a polar covalent bond, here I'm really thinking about tug-of-war between the seniors and the freshmen. The seniors are going to be bigger, they're going to be stronger, they're going to be able to pull a little bit more strongly on that rope than the freshmen are. And because there's an unequal pull on the rope, such as in a tug-of-war game, or an unequal pull on the electrons in the bond, that's what causes that polarity. So most bonds actually exhibit a kind of blend of characteristics of ionic and covalent bonds. They're usually not super black and white, but there is one way for us to kind of decide about what kind of bond we have, what bond type it is. And so the way we do that is we actually use electronegativity again. So the difference, so we're looking at the second bullet point down here. So the difference, right, that's a subtraction problem. So the difference between the electronegativities of two atoms in a bond can determine the bond type. And if that difference falls between 0, let's change that color. So if that difference falls between 0 and 0.3, we're looking at nonpolar covalent bonds. If the difference falls between 0.3 and 1.7, we're looking at polar covalent bonds, according to this table over here. And if we are looking from 1.7 to 3.3, what we're really looking at is going to be an ionic bond. So here I want you to use the electronegativities that are provided in the periodic table here to calculate the difference of the atoms that make up the three compounds that we're looking at on the left here, and I want you to determine the bond type. We'll go ahead and do the first one together. So chlorine remember, is a diatomic element. That's why it's Cl2, because when it's by itself, it naturally pairs up. So chlorine has an electronegativity of 3.0, and we're looking at the difference. So we're going to do 3.0 minus 3.0, which equals 0. So the bond type for chlorine is going to be a nonpolar covalent bond. Now I want you to go ahead and try and do the same thing for numbers 2 and 3, hydrochloric acid and sodium chloride. And then you're done with this video.